let assume that G admits no non-trivial characters defined over that means that there is no homomorphism of the group G into GL1 which is defined over Q, morphism defined over Q, characters defined over Q. Then GR, this means okay, modulo, oh yeah, sorry, G intersection GLNR modulo GZ, which by definition is G intersection GLNZ, has finite admission. Moreover, GR by GZ is compact if and only if GZ has no unipotent elements. This is equivalent to saying, same as saying GQ has no unipotent elements. See, if GQ has a unipotent element, then GZ also has a unipotent element for the following reason. So, if U in GQ is unipotent, that means all eigenvalues are 1, which also means U minus 1 is nilpotent. And in fact, you can define the logarithm of U, let me call it x equal to log U can be defined as using the usual logarithmic series. Write U as U minus 1 plus 1, this is 1 plus U minus 1, so you can expand in a power series, but it terminates because U minus 1 is nilpotent. So log U, x equal to log U makes sense, sigma minus 1 power n minus 1 power r, U minus 1 power r equal to 0 to infinity. It actually terminates, though I write 0 to infinity. Then you find that U is nothing but exponential of x. Okay, now if U is a rational matrix, X is also a rational matrix because this is a finite series. This falls into M and Q. And U equal to exponential x. So if you write U power r is exponential Rx, which is 1 plus Rx plus r square by 2 factorial square, etc. Some terminate somewhere. So it can't go beyond n clearly. So r power n, x power n minus 1 by n minus 1 factorial. So x per x square etc. x per n minus 1 will have bounded denominators when you write them as rational matrix. So when you make R sufficiently large, make it divide and make R the least common multiple of all those things, and then you find this becomes integral matrix, and this is obviously unipotent again. So if you have an integral matrix, if you have a rational matrix which is unipotent, there is also an integral matrix which is unipotent, and of course conversely. Okay, so this is a theorem I am after, but in fact I will begin with this second statement, which of course implies, in that case it implies that the quotient is finite Harmatian. If this condition is not satisfied, the quotient is not compact, and then of course it's more difficult to say that it has finite Harmatian. But we have already seen one example where G equal to SL and R. There we have seen SL and R by SL and Z as finite Harmatian. Okay, now so I'll take the second statement. Star is known as Goodman criterion for co-compactness. Goodman criterion. He conjectured it, so it's named after him. The statement. Firstly, proof of star I am embarking on now. First reduction, one can, let's see, any algebraic group has a maximal normal nilpotent maximal unipotent subgroup. G algebraic group, I am not saying anything about the field of definition, then one can always talk of let RUG be a maximal normal nilpotent unipotent subgroup of G. Unipotent means every element is unipotent. Now, I said be a maximal, not necessary. There is a unique maximal one. If you have two unipotent groups, one normalizing the other, then together they will generate a unipotent group. This comes, it's a little, I mean, strictly speaking, we need what is called Engel's theorem, which I hope some of you are familiar with. It says if you have a Lie algebra of nilpotent matrices, then it's they can simultaneously, they can all be put in triangular form. If you have Lie algebra of nilpotent matrices, that's the statement. So, and that is applicable here because if you use a unipotent group, any closed subgroup, any algebraic group is a Lie group, and once you know it's a Lie group, you can the Lie algebra of the unipotent group consists of logarithms of various. It's a subgroup of GLN, so you are taking logarithms of those are the things you are going to get, and they are all nilpotent. So they can be simultaneously triangularized. That's the statement. So from that, it's easy to see that RUG, you can talk of the maximal normal unipotent subgroup. This is usually called the RUG is the unipotent radical of G. You put the R in front because in the French they say radical unipotent, so it's the other way. So that's why RU rather than UR. And much of this was developed by French mathematicians to begin with. So, RUG is the unipotent radical of G. Then you have a natural map G . Now, turns out that this quotient is again an algebraic group. natural fashion. I'll come to this in a moment. And if G is defined over Q over any field K, C, so is RUG and G modulo RUG. These are standard theorems from algebraic groups. I don't think I'll go into the proofs. You can find proofs in Borel's book on linear algebraic groups or Springer linear algebraic groups. Now, let me also make here G is a algebraic group over a field K. Look at the, so G is, my definition of algebraic group says it's a subgroup of GLN C, which is also a set of zeros of a bunch of polynomials in the matrix entries and the determinant inverted. G in GLN C. Then the Lie algebra of G. So G is a necessarily a Lie group, Lie subgroup. It's a closed subgroup, therefore a Lie subgroup. The Lie algebra of G of G is again defined over K. What do I mean by this? You have G is going to sit as a subalgebra in M and C, which is the Lie algebra of GL and C, sitting inside here. And in here you have M and K. K is a subfield of C, so you have inclusion here. What we mean here is G is the linear span of G intersection M and K. This G intersection M and K will be a Lie algebra over K, because G is a Lie algebra, so the intersection is going to be Lie algebra, but defined over K. That's it's a basis in which the structural constants are all in K. So, and then you recover the big Lie algebra by simply taking GK. Sorry, G equal to linear span. Yeah, this is linear span G. This I'll call GK, and call them the K points of the Lie algebra G. So when you have an algebraic group defined over K, its Lie algebra is also defined over K. And here you have a situation, you have G RUG and so the group G, let me write this. You group G and its Lie algebra, that is, incidentally, that's German G. So I'll keep saying G for that also. And you have RUG as for Lie algebra, RU. And let me denote G by RUG. It's a group which I'll call B. And its Lie algebra I'll denote by B. G by RUG, the group B has no unipotent normal subgroup. Once I pass the quotient by the unipotent radical, you have no more, because if you take the quotient, if you take a unipotent group, if there's a unipotent normal subgroup, you can take its inverse image under this map, you will get a bigger unipotent group, contradicting the maximality. Okay. I already said that B is defined over K, and I'll make a definition. An algebraic group G is reductive if RUG is trivial. So this group B is reductive, this sets. And that unfortunately I will have to once again assume something more about algebraic groups. B reductive, yeah, first let me make a definition. Another definition, a torus is an algebraic group isomorphic over isomorphic to the group of diagonal matrices in GLR C for some R, or equivalently a torus T. T is isomorphic to product GL1 C. Here you have some R factors. R4 product of GL1 C, C star cross C star cross C star times that's what a torus is. A torus can be defined over K, but may not be isomorphic with this product over K. That can happen. So we make a special definition. If you have a torus T defined over the field K in C is K split if T is isomorphic with GL1C per R over K. This GL1C per R is a natural structure of an algebraic group over K. In fact, over Q itself, if you like, and therefore for every field containing Q. If T is isomorphic to this over K, then you call T a K split torus. So T breaks up into a product of one dimensional groups, each one dimensional group being isomorphic to C star over K. There are lots of examples of non-split tori. Let me illustrate this. Let's look at K equal to R, and then I look at the group SO2, which is by definition set of elements T in GL2C transpose T equal to identity. I claim that SO2, this is the definition obviously over R, in fact even over Q if you like. So I say claim that this SO2, this group SO2 is not split over R. Notice over C, this is a torus. It simply becomes C star cross C star because this is something which leaves in the quadratic form x square plus y square. But over complex numbers, this quadratic form is same as xy. If you look at the things which leave invariant xy, the quadratic form in two variables, that's going to be TT inverse. With determinant 1, that's going to be. So over complex numbers, this is really a torus. It's a torus because over complex numbers, it's isomorphic to C star, it's one dimensional torus. But what happens over reals? Suppose it's isomorphic to GL1 over reals, then the real points will be isomorphic to real points. But SO2 real points is what? They consist of points of the form cos t sin t minus sin t cos t. The orthogonal group that's how it looks, and that is a compact group. The orthogonal group of say R points in one case is compact, in the other case it's non-compact. It's the whole of R star. Its elements in diagonal matrices which are real entries, which means it's isomorphic to R star. So if it's so SO2R is compact, but GL1 R is not. When I say it's an isomorphism, it will automatically be an isomorphism. It's an algebraic isomorphism, it will automatically be an isomorphism to corresponding topological groups. So if one is compact and the other is non-compact, obviously they are not going to be isomorphic. This is a typical example. Obviously, this SO2 is even defined over Q, as I said, and if it's not split over R, it's not going to be split over Q either. Any smaller field, it's not going to split. Any field containing R. So one further last definition is the following. Before I make the definition, let me point out something else. What are the characters on GL1? That is, I am looking for morphisms of GL1. GL1. Algebraic group morphisms. That really means you have a group homomorphism, which is a polynomial map in the variables z and z inverse. I mean t and t inverse, it has to be a polynomial map. And only polynomial maps are the kind which goes from C star to C star. Any character C star is of the form for some R in you want a map which is polynomial in Z and Z inverse, and if you demand that, these are the only maps. The only homomorphism we know, C star is nothing but S1 cross R. Okay, C star is nothing but S1 cross R, and S1 will have to go into S1 because S1 can be characterized as the maximal compact subgroup of C star. So S1 will have to go into S1. S1 the map will have to be, there is only one automorphism to the circle. Only mapping the circle into itself are of this kind, Z to Z power R. And then if you want an algebraic extension, this is the only possible algebraic extension. It's raising to the power R on the circle, therefore it's also raising to the power R in the whole complex plane minus 0. So a torus, if T is a torus over K, T admits a maximal K split subtorus. If you have a torus T1, I mean suppose T1, T2 are subtori, when I say something is K split, it means automatically it is defined over K. You have two subtori defined over K, then you can form the group T1 times T2. Okay. That will give you a new torus which will also be K split. It requires little work to see that it's also K split. Already on T1 there are characters, on T2 also there are characters. If you look at T1 intersection T2, it's either the two coincide or or the common portion will be some another, the connected component will be some torus, and the connected component will have some index. If you raise things to the power, then you get characters on both. Once you get some characters which will distinguish points, well, it requires a little bit more. What you find is you get all characters which belong to a subgroup of finite index in this set of characters. So let me also say here, the group xt of characters is isomorphic to G L, where L is dimension of the torus.
If T is split. If T is split.
I'm not saying character. I'm not making anything about definition over K.
Okay.
Xt is characters on K. and then I write xkt to be characters.
Defined over
This is guys some z q with q less than k. These are characters defined over. And it's not difficult to see that this is same as this q is the dimension of a maximal of the maximal k split torus. Basically, the tori can be understood in the following fashion. If you want to understand all tori over a field K, the way you go about it is the torus is completely given by, the over algebraic closure, the torus is completely determined by this character group. If you like, the torus T can be recovered as home xt. This is going to be a free abelian group on q elements. So for each element in the q, you just have to fix one element C star and then it extends to home of. And conversely, T can be identified with this. And so, over the complex numbers, you know what T is once you know what xt is. Now, if it's something defined over a field K, then you can look at all automorphisms of complex numbers which fix K. I don't want to call it Galois group because C is not algebraic over K, but it's like the Galois group. We take all automorphisms of that. Now, notice that the automorphisms operate, automorphisms of C over K acts on xt. How do I say that? See, T, you have, suppose you have an element sigma, automorphism C over K. You can look at T of C, which is of course contained in some GL and C, and on GL and C, the Galois this group operates, or C over K operates on entry wise. You can make it operate, so it operates. And now my T is defined over K, which means it's given by a bunch of polynomials which have coefficients in K. But if a certain matrix, if these polynomials vanish on a matrix, the Galois conjugate of the polynomial also vanishes on the same matrix, because the polynomial is only coefficients, it's the same polynomial with Galois. From that it becomes clear that Tc is stable in the Galois group. So now you look at the following, take an element chi in xt, and chi is a homomorphism from T into complex numbers, but then you can first on T you can operate by the element sigma inverse composed with sigma. Sigma inverse operates on Tc, chi takes Tc into C star, and sigma operates on C star. So if you do that, you get an operation of the Galois group on the space xt. So xt has action together with action of Galois, I'll call it G C over K. This pair, from that pair you can recover T. That's all. The point is this: how do you recover T? You, after all, T over complex numbers is nothing but this home xt C star. On this, this Galois group operates. So this, when you identify with T, these are simply set of how do I say this? Yeah. Well, how do I? So given a torus defined over K, you get this data, this pair, and you can go in the converse direction. I am a little confused about how to say it, but it's not difficult. You should be able to work it out yourself how to see how to get the thing out. Yeah. Okay. Now, so and finally I make a definition. A torus T is anisotropic if it admits anisotropic T over K is anisotropic over K if it admits no characters or non-trivial characters. Okay, that's an anisotropic torus. So going back to the Goodman criterion, what we wanted to show is that if Gk admits no unipotent elements, then Gr by Gz is compact. That's what we wanted to prove. We'll now first reduce the problem to the case when the group G is reductive. That is, it has no non-trivial, normal unipotent subgroup. Okay. And then, so the first reduction is to say so Goodman criterion again. For G can be reduced to that for G modulo RUG, what I call B. How does it go? You see, you have this mapping. First let me remark here that a unipotent group admits no non-trivial character. This is a consequence of the following fact. If G is an algebraic group defined over fielded as unimportant algebraic group, and phi G to H is a morphism of algebraic groups, then if X in G is unipotent, so is X. Unipotent elements will go into unipotent elements, and similarly semisimple elements, semisimple matrices will go into semisimple matrices under this map. X is semisimple implies phi X is semisimple. In fact, the Jordan decomposition of any element into a product of semisimple and unipotent elements carries over under phi. If X S into XU is the Jordan decomposition into semisimple and unipotent parts, then phi X S into phi XU is the Jordan decomposition for phi X. These are again standard results and not so difficult to prove either, but the standard reference for you is Borel's book, and maybe slightly Borel's book is not the best reference. Maybe Springer's book is a better reference. Springer is also a book on linear algebra groups, published by Birkhauser. Must be available in the library. So that is the see the entire theory of linear algebra groups was first developed by Chevalier, and then the Borel stepped in and he really made big advances. Between Chevalier and Borel, the theory was fixed up, and of course later Grothendieck stepped in and he proved many things which could not be proved by older techniques of Borel and Chevalier. That guy really again revolutionized algebraic groups, like he did algebraic geometry in general. Anyway, but there is no real account of algebra groups in a scheme theoretic fashion, except there's this book by Demesur and Gabriel. It's an encyclopedic book, but doesn't get far. It confines itself to essentially Abelian algebraic groups. I think it goes on and on and on. Of course, maybe they do talk about. I don't think they even talk about nilpotent groups. A lot of time is spent on finite group schemes, stuff like that. Anyway, sorry.
Waterhouse. There's a book.
I don't know this book. If you recommend it, by all means do. See, I have a tendency to go back to books which were there in my graduate school days. So, subsequent books I have not had a look at because, well, for some reasons, not those books are adequate for me. So I have not had. Okay, so all this is, and from this, of course, it follows that if you take a character on a unipotent group, it has to be trivial because it will take a unipotent element into a unipotent element. But in a torus, there are no unipotent elements. Diagonal matrices have no unipotent elements, so it has to be trivial. So all characters on a unipotent group, any unipotent group admits no non-trivial character. Okay, now let me get down. Say that it can be reduced to the case RUG. For this, I will state a lemma. If U is unipotent defined over Q, then U by UZ is compact. UR by UZ. As you can expect, this can be proved by an induction on the dimension of U. The simplest unipotent group, of course, by induction, dimension U equal to 1 will mean U is isomorphic to then what happens? You see that UZ is Z, is isomorphic to Z, and is sitting inside UR it's a standard fact that you reduce the case when R by Z is compact. So you have to first, of course, that requires a little bit of work here to prove that if you have an unipotent group defined over Q of dimension 1, it's necessarily. More generally, if you yeah, so now what you do is the following: you take any general U admits a filtration U equal to U0 containing U1 containing U2 UR ur plus 1 equal to 1 such that ui are defined over q ui by ui plus 1 dimension ui by ui plus 1 so once you admit such and ui normal in ui plus 1 normal in ui. So a sequence of subgroups each normal in the preceding and the quotient one dimensional. So we start with ur which is one dimensional. So we know that ur by uz is compact and then so that's the start of the induction which is r by z being compact and then suppose you have proved it up to ui and you are going to look at ui by ui plus 1. Yes, suppose you proved it for ui plus 1, you have this sequence ui plus 1 to ui by ui plus 1. Notice that ui plus 1 is normal, so you have this sequence with this mapping surjective with this as the kernel. Now I know that ui plus 1 intersection ui plus 1 r intersection ui plus 1 z is compact, okay, and I know that the quotient is compact. You have a situation a locally compact group and a discrete subgroup here. The image of the discrete group is co-compact here. The intersection is co-compact here. Now it's a simple topological argument to tell you that ui by ui z is also ui r by ui z is compact. So you find that you have also this sequence which is exact if you like ui plus 1 r to ui r points to ui by ui plus 1. This sequence is exact and you look at ui z here. In general, the image of ui z will not map onto ui plus 1 z, but will map into a subgroup of finite index, which is why we defined arithmetic groups in, as commensurable, not necessarily. The point is that when you take this map, it's a polynomial map with coefficients in q, and there may be denominators. So some integral matrices may not go into integral matrix, but if you go to a sufficiently deep congruence group, that will happen. So it will go into subgroup of finite index here. That quotient is compact, and here the intersection will be ui plus 1 z. By induction hypothesis, this quotient is compact, and therefore it is easy to conclude that this quotient is also compact. The thing caught between, the quotient is again compact. That's pure set topological argument. Once this is done, sorry? Well, good question. How do I answer that? Well, the point is, see, this is a look at the I have to prove its mapping surjective. Well, yeah, one way of doing it is that you can take this Lie algebras and you will get for this one a basis which is in Q x1, and then for for this you will get a base one dimensional basis, and then you step by step make a basis starting with you choose a basis with the following point x1 x2 xr basis in Lie algebra of u q such that xi etc xr is the basis of ui, and then look at their exponentials, then you will see what's happening. In a any element of u0 can be written as a product t1 x1 times t2 x2 etc. This is the property of unipotent groups. Any element in the group can be written as exponential of t1 x1 times exponential of t2 etc. exponential of tr xr. use that fact and then it becomes clear, it becomes subjective. I think I started at the wrong end. I start ui by which way is it? Which is bigger? Ui is bigger than ui plus 1, right? Yeah, right, okay. Okay, this takes care of the unipotent case, which of course any unipotent group admits no characters over K. So in that case, I think I goofed a little bit. Okay. Did I assume that when I said Goodman criterion, I have to assume that the group is reductive. The Goodman criterion says that if the group is reductive and does not admit any unipotent elements, then the quotient is compact. It's only for reductive groups. If and only if is a statement I made, assuming that G is reductive. If G is not reductive, here is an example. G is not, U is a unipotent group, the quotient is compact, but it's okay. It admits lots of unipotent, every element is unipotent in fact. So I should have said, in my statement, it has been corrected. If G is reductive, then when I first stated it, I didn't have the definition of reductive group. So I had tacitly assumed I was talking about reductive groups. For reductive groups, statement I made is right. So let me restate the whole thing. The Goodman criterion says the following. Let G be an algebraic group over Q. Then GR by GZ is compact if and only if G by RUG Q has no unipotent elements. That's the correct formulation. GR by GZ, G algebraic group over Q, and admitting this no non-trivial characters over Q. So G is an algebraic group which admits no non-trivial characters over Q, and in addition, so it's compact if and only if, then GR by GZ is compact if and only if this group G by RUG, which I call B for instance, it's a reductive group. It's such that its Q points admits no non-trivial unipotent. Identity of obvious unipotent element, so I should say non-trivial unipotents. Any unipotent group, the quotient is automatically compact. UR by UZ is compact, so that has to be. So just to allow that, I have to go to the quotient and say it's only for the reductive group the statement is correct. Sorry about that. Okay. Okay. So this is the Goodman criterion. Now I have told you first, I need another fact. If G is reductive, that is RUG is trivial, then G is necessarily the form, let me also assume connected, well, okay, G, let me assume that G is connected and reductive, G connected, then G is necessarily the form, or let me put it like this, G reductive, then the identity connected component G0 of G is of the form T times S, where T is a torus over K defined over K, and G T is connected semi-simple and defined over K.
S is connected.
Oh yes, sir. T S will T is connected semi-simple. Semi-simple means the Lie algebra is semi-simple. I don't know if people are familiar with this, or should I say something more about it? No, maybe I'll say what semi-simple Lie algebra is. Okay, it's the Lie algebra. Semi-simplicity is nothing to do with the field of definition. You will see. A Lie algebra over any field F is semi-simple if it admits no non-zero abelian ideal. Abelian means all bracket operations are 0. Ideal means you take an element in the big, you take an element x in the ideal and y in the big algebra. The bracket should be in the ideal, as you will do with rings, do Lie algebras. It admits no non-zero abelian ideal. It's same thing as saying it admits no nilpotent, non-zero nilpotent ideal. The same thing as saying it admits no soluble ideal. It's clear that if it admits no non-zero ideal, it cannot admit any non-nilpotent ideal, and it's also clear if it admits no soluble ideals, because soluble implies nilpotent. I mean, sorry, the other way around. Abelian implies nilpotent, nilpotent implies soluble. On the other hand, if it does not admit any, suppose it does not admit any soluble ideal, take that ideal and keep taking brackets. Take the descending take the derived series. At some point, you are going to end up in an abelian ideal. And since all the elements of derived series are characteristic ideals, they are ideals in the bigger thing. So you find it's you end up with an abelian ideal. Same thing with nilpotent. So, but the most an important theorem which gives you a criterion for that, which is valid only in characteristic 0, if characteristic f equals 0, then semi-simplicity, Lie algebra is semi-simple if and only if the trace form, as this presently it's called the killing form. The killing form of G is non-degenerate. What's the killing form? Killing was a German mathematician. So it's named after him and not has nothing to do with killing. See, if your Lie algebra G over the field F, then you have a nice representation. One has then a Lie algebra homomorphism called add, which goes from G into endomorphisms of G as a vector space. This is a Lie algebra in its own right. It's simply Mn. If you fix the basis, is nothing but Mn F, sorry, where you have the bracket operation AB minus BA makes it into Lie algebra. And what this means is that this add is homomorphism from G to end F. How do you get this map? So you have to define add X as a mapping of G to G. And there is essentially only one way you can do it. You want to add X, you want to define add X on Y, simply bracket XY. And the Jacobi identity tells you that this is a homomorphism of Lie algebras. Add is a homomorphism of Lie algebras. Now, for any endomorphism, you can define the trace. And the killing form is a bilinear form. G cross G to the field F, which tells you K, defined as follows: Kg is a Kg of xy, is trace add x, add y. Add y is an endomorphism, add x is an endomorphism, compose the two, you get a new endomorphism which is add x, add y, and I take the trace of that. This is known as the killing form of the Lie algebra G. Our G, we are looking at finite dimensional vector spaces. This is a bilinear form, and notice that since trace xy is trace yx, it is a symmetric bilinear form. If the Lie algebra is unipotent, for instance, then this is identically 0 because add x, add y become nilpotent elements. Any composite, you can simultaneously make them triangular because of Enger's theorem, and therefore add x, add y is triangular, which is 0 on the, therefore it is 0, identically 0. So this tells you that anyway, so this is symmetric bilinear form, and the notion of non-degeneracy, Kg non-degenerate means Kg xy equals 0 for every y in G implies x equals 0. If x is non-zero, there must be some y such that Kg xy is non-zero. And it's symmetric, so you can interchange roles of x and y there. So, and it's a deep theorem that a Lie algebra is semisimple if and only if the trace form is non-degenerate. Its killing form is non-degenerate. It's a theorem due to Cartan. It's a relatively deep result. I don't think I can go into the proof. You will find it in any good book on Lie algebras. Again, I suppose Sayre's book on algebra Lie. It's in the translation available in English, right? It's done all over complex numbers, but that does not matter. Just go through. There's the Bourbaki volume on Lie algebra, which also tells you.
Characteristic 0.
Characteristic 0 is important. I've said that already. I've said it.
Characteristic 0 there.
Yeah. If characteristic is not 0, it's not true. In fact, already it falls for SL2. In for if G equals f of characteristic 2, G equal to SL2, the algebra 2 cross 2 matrix 2. You can easily see that Kg is degenerate. In fact, diagonal matrices with the algebra of SL2 is nothing but trace 0 matrices. Notice that the diagonal scalar matrix 1 1 is of trace 0 in characteristic 2. That turns out to be orthogonal to every the central element. Add x is therefore 0 for that element. So trace add x add y is 0. Yeah. Okay, so here is the Goodman criterion which I am after. G is an algebraic group defined over Q, admitting no non-trivial characters over Q. Then Gr by Gz is compact if and only if G by Rug, this is the semisimple quotient B, which is a reductive group, has no non-trivial semisimple elements. First, so I want to reduce the problem. So I have G here, G by Rug, which I call B. This is an algebraic group defined over Q, and this is a morphism defined over Q. It's a surjective morphism, and the kernel is RUB. This is exact. More, this sequence splits. There exists R from B to G defined over Q if it's over K. If this is all G defined over K, then K is any field containing complex numbers. You have mapping B to G defined over K such that phi composed with R is identical. R is also defined over K. Once again, if you take a arithmetic group of this, take its image. So sorry, if you take a look at Gz, then you have the image under pi goes into pi Gz, and your kernel, which is RUG. This may not be onto, but goes onto a subgroup of finite index. And we know that it goes onto a subgroup of finite index. And what is more, you look at RUGZ times R of pi z. This will be it may not be subgroup of GZ, but this will become commensurable with GZ. Intersection GZ has finite index both. Once again, it's the same kind of argument. R is polynomial with coefficients in K, and then you go to a sufficiently deep ideal, then all the elements in that congruent subgroup will map into integral elements. You can work with them if you like. That times replace R pi z by some subgroup of finite index, pi z by some subgroup of finite index, and then this will be a subgroup of finite index in Gz. That's the way it works. Okay.
Is it true for subjective now?
Sorry?
Subjective group also.
Yeah, if it's defined over K, even then, I mean, to prove that the image is an arithmetic group, that's okay. But you can't get a retraction. You can't get a mapping like this, the other direction in general.
So what I'm saying is, suppose you have G group over Q and then another subjective Q map, then arithmetic group will go to a
Yeah, that basically the same proof. Take see, the point is that you have to be a little careful. It is true, but actually it's a little more delicate. Yeah, I'll have to. Yeah, sorry, it's a little delicate, and that requires some kind of proof. We'll come to that. I'll be handling that at some point. You'll see. Okay. So, in fact, even when it's suppose you take a surjective map with finite kernel, even then it's a little delicate. You have to, even in that case, it's not clear that an arithmetic group will go into onto an arithmetic group. That's true, but it requires a little proof. We'll see. Okay, RUGZ, and this means since we know that RUG, now take K equal to Q. Since we know that RUG by RUGZ lecture I by mistake I tapped it by mistake. I didn't mean to. Okay. Sorry. This is is compact. So, if you knew that G by RUG modulo its integral points is compact, then G by RUG R real points modulo its integral points is compact, then this will follow. So, the point is that so because of this implies can assume G to be reductive. I am looking for a criterion for the quotient being compact. For the RUG, we know that the quotient is compact anyway, so you can pass the quotient, and so the problem reduces to the case of this. Notice that yeah, if in the quotient, for the quotient, suppose I prove the statement. After all, I am making the statement only for the quotient, that it should have no non-trivial unipotent elements. So this is okay. Can I assume G to be reductive? So I have to prove the theorem for the reductive groups. Once again, G, as I already told you, is of the form the torus times semisimple T defined over K defined over Q, and the no characters, no non-trivial characters on G implies no non-trivial characters on T. The reason is the following. You look at G is now T times S, pass the quotient by S. I said when I said T times S, T and S, when I write G as T times S, I mean T and S as normal subgroups, and they commute with each other. I look at G by S. This is the quotient of T. T is contained in G. I have a natural map G to S, and yeah, I must also point out that T intersection S is a Lie subgroup, is a closed subgroup, it's a Lie subgroup. Its Lie algebra has to be trivial because its Lie algebra is abelian, and our assumption is that S has no abelian ideals. This intersection will be an ideal in S, and we have assumed that the Lie algebra has no abelian ideals. S is semisimple. So T intersection S is therefore an algebraic group with a Lie group whose Lie algebra is trivial. So this means this is finite. T intersection is the Lie group with Lie algebra trivial, therefore it's a discrete thing, but it's also an algebraic group. An algebraic group which is discrete is necessarily finite. So, this mapping P has finite kernel. T maps onto G by S, and this is an isomorphism, I mean modulo the kernel. But if I take diagonal matrices, what are the subgroups of diagonal matrices? What are the finite subgroups of diagonal matrices? any finite subgroup some power is going to vanish. So you can look at elements if the finite group is of order R, look at the set of elements of order R, the quotient is a torus and that will be a further quotient of G by S. The quotient is again is it again a torus of the same dimensions, so it will have plenty of non-trivial characters, therefore G by S will also have non-trivial characters if T has non-trivial characters. If T admits non-trivial characters, so does G by S. But G by S admits means G admits non-trivial characters. Implies G admits non-trivial characters. Now we will prove the theorem in the case when G is a torus. If I do that, in the case of torus, every element is semi-simple. So what I have to prove is if a torus admits no non-trivial characters, then Tr by Tz is compact, because every element of T, even over complex numbers, is semi-simple. There are no unipotent elements in a torus. Torus consists of diagonal matrices. Over complex numbers, it's the product of diagonal matrices. Diagonal matrix is semi-simple. Okay, T is isomorphic to diagonal matrices for some GL, and therefore every element is semi-simple. So there are no unipotent elements. So if G happens to be T, I will have to prove that Tr by Tz is compact. There is no further condition. It's automatically true that it has no unipotent elements. So I will split it into two parts, one for the torus and then one for the semi-simple group, because you can pass the quotient to the torus and then you get a semi-simple group. The torus itself, if the theorem is true, the quotient is compact, and exactly as before we have argued like this, in the quotient it's enough to prove for the quotient. So suffices to prove the theorem separately. For the case of G equals to torus or G semi-simple. Let us take up the case of the torus first. Okay, T is a torus sitting inside I take the case of torus first. Or maybe in one step I can do the whole thing. Or maybe do it in one step for G reductive. Hold on, this is getting a bit confused. Okay, no, I think I won't separate the two cases. I'll do it in one step. Anyway, it's true that you can suffice to prove in these separate cases, but let me see. Okay, so what do I do here? I have this group G and its Lie algebra G. This is defined over Q. So I choose look at the mapping, add from G to GLG. This is defined over Q.
So you're doing simultaneously.
Yeah. See, I don't know. Midway through, I may find I've landed in some difficulty and I may change gears. But at this point, I'm thinking I'll do it. It's defined over Q. What I'm going to say will work for the semi-simple case, definitely. If it doesn't work in the reductive case, then I'll come back and do the torus separately.
But you have already shown that T is anisotropic, right? Therefore, TR is compact, and we are done.
No. TR is Q
Yeah,
and
no, it's anisotropic over Q, not compact. In fact, a consequence of that is the Dirichlet unit theorem. We'll see later. This is a thing defined over Q. Okay. Yeah. So you have mapping, and you can you can think of G as Cn with respect to a basis of GQ over Q. Fix a basis of GQ over Q and treat it as the basis of, think of this as n-dimensional vector space Cn. Well, okay, see, let me see. Now, so look at G, the subgroup of GLG. It's an algebraic subgroup defined over. Again, if you have a morphism of an algebraic group G into another algebraic group H defined over Q, the image is an algebraic subgroup which is defined over Q. Okay. So F G to H morphism over a field K, then I'm always talking about characteristic 0. Fg is an algebraic subgroup of H over K. Notice that at G is contained in SLF because there are no characters on at G. If any character on any non-trivial character on at G will give you a character on G itself by composing. There are no non-trivial characters. Therefore, determinant, which is a character on G, G to determinant G is a character on at G defined over K and hence trivial. So determinant is 1, so it goes into SLG. Now I look at the mapping. Let me give this a name. At G is, let me call it H. I look at H over HZ into SLG by SLGZ. You have a natural map like this. It's an inclusion. And I will prove that the image is necessarily compact. And the mapping is a homeomorphism onto the image, which will prove that H over HZ is compact. HR, sorry. Now we have I'll prove the image is first relatively compact. Why is it relatively compact? It's the first question that comes. Image is a natural map. Image IH is relatively compact. Why is this true? We proved a criterion for relative compactness, for a criterion for some sequence going off to infinity, mod. This is some SL NR, MR by SL MZ. We gave a criterion for this to go to compact. What is the condition? The condition is that a sequence Hn in H tends to infinity mod SLGZ if and only if there exists sequence phi n in SLGZ such that add a sequence Hn add call it H, okay, Hn phi n Hn phi n tends to 0. Now these elements phi n are endomorphisms of the Lie algebra GZ of the
Pn in GZ.
huh?
It should be in GZ, not SL.
So, sorry, yeah, in GZ. Thanks. Should be GZ such that lattice points. Now phi n are elements in. This is the same as endomorphisms. Sorry, it should be. I should say endomorphisms of. Everywhere it should be. Add G goes into, when I say SLV, endomorphisms of these are elements of SL GZ, and that phi n is that means an element of endomorphisms of GZ. An element of SL GZ is an automorphism of GZ, and the Lie algebra element corresponding Lie algebra element is phi n in GZ.
You're applying Mahler's criterion.
I want to do that. I am applying Mahler criterion. Mahler criterion says this goes to infinity if only there exists a sequence like this. If there is a sequence phi n of points, see, my vector space is G, GZ, and an element of it's in phi in GZ, sorry, okay, but then I can look at add phi n. In the Lie algebra, you have elements. I look at add phi n. This is in endomorphisms of GZ. And what I know is Hn phi n tends to 0. That means Hn actually is add of something, add of Hn prime, which means therefore what happens is this. How does add Hn prime operate on phi n? Think of Hn prime, add Hn prime as a endomorphism. This is the same thing as in fact, I don't have to go through this. Hn is add Hn prime. What I want to say is this following: Hn phi n, Hn phi n. This is an element of the Lie algebra. I want to see what add of Hn phi n is. This is Hn add phi n, Hn inverse. That's the essentially definition of adjoint representation. Adjoint representation, how does it operate? It operates by conjugation on the group and therefore on the induced map on the Lie algebra. So, which is also conjugation. So, this is how it works. Hn add phi n, Hn inverse. So, this we know tends to 0. So, if you look at the rth coefficient of the characteristic polynomial of add phi n that goes to 0 for r greater than or equal to 0th coefficient won't be, I mean r less than or equal to dimension g.
You are applying a criteria which is there in your book. G naught gamma, Gn gamma goes to infinity.
This is that Mahler criterion is precisely that. I mean, Mahler criterion, without if you don't talk of arithmetic groups, that's the kind of criterion one groups. Why we call them L subgroups and so on. I'll come to that later.
No, but in your book, G naught gamma, Gn gamma goes to infinity. Even only if there is a gamma and not equal to identity, so that Gn gamma.
Yeah,
Gn
right.
inverse
Goes to identity, but this is the Lie algebra version.
Yeah.
Instead of elements in the group, I'm looking at elements in the Lie algebra.
Yeah, so that's why you are taking this add.
Yeah.
What do you mean by add Phi? And Phi is a lattice process.
Phi n in the Lie algebra. It's in the Lie algebra.
Okay.
Add of any element in the Lie algebra makes sense. Add phi n makes sense.
Why you try this Lie bracket? You know.
Yeah. Add x of y is bracket xy. The characteristic polynomial add phi n goes to 0. But add phi n are integral matrices. Therefore, the characteristic polynomial is an integer. The coefficients of the characteristic polynomial are integers. Integers going to 0 means they must be eventually 0. So all the coefficients of the characteristic polynomial are 0, which can happen only if it's a nilpotent matrix. All the eigenvalues have to be 0, so it has to be a nilpotent matrix. So add phi n is nilpotent. Since they are integral. In fact, it's the same integer all the time because the characteristic some integer phi n is integral. Hn add hn phi n hn inverse has also to be integral. So the coefficients of the characteristic polynomial have to be integral. On the other hand, they go to 0 because this goes to 0. Implies that add phi n is nilpotent for all large n, which implies exponential phi n will go to is unipotent for large n and non-zero. Phi n are non-zero, so exponential phi n will be unipotent and non-zero in G for large n. Okay, so this shows that a contradiction. Therefore, why is this a contradiction? Phi n is not it. So this implies all this implies add G R by add G Z is relatively compact in SLGZ, SLGR modulo SLGZ.
So that should be exponential at.
Yeah. So all this goes to show that add GR modulo add GZ is relatively compact in SLGR by SLGZ. Okay. So you find that the image IH H is at G image IH is relatively compact in SLGR by SLGZ. So far that's the conclusion. Okay, now we, on the other hand, we are interested in the map H. Yeah, for, the next claim is image is closed. This follows along the same lines. I proved something similar when I was dealing with the SYN1 modulo gamma, the image is closed and so on. And proof is here similar. The point is there we had a description of SYN1 as something which is leaving invariant a certain quadratic form, or rather something which fixes some vector in some representation. We have a similar theorem here which I have to invoke, namely the theorem from algebraic groups. G algebraic group over K, H algebraic subgroup over K, subgroup of G also over K. Then there exists a representation rho from G to GLV over K, V a vector space over K, and a vector a vector V naught in Vk and a character chi over K on H such that H is precisely the subgroup which fixes the one dimensional line through V naught. Set of vectors G in G with the property that rho G V naught equal to chi G V naught. Any algebraic subgroup is precisely the isotropy of a line in some representation. Everything over K. If the subgroup is defined over K, you can find a representation over K, that's a homomorphism to some GLV over K, and a vector in that vector space such that the line through that vector, the unique line through that vector, the isotropy of that line is precisely the group H. Okay. In the special case when H admits no character over K, it becomes isotropy of that vector itself. Sorry? Huh? No, where is the question of algebraically close? The points you are looking at are over algebraically closed field, doesn't matter. It's over C. Everything is over C. But the vector V naught must be a K rational vector, a K point. And the line through V naught is a line defined over K. It's a vector space. You can talk of if a vector space is defined over K, then you can talk of subspaces which are defined over K, in particular line defined over K. So I have a line defined over K such that the isotropy of that line for the action of the group G happens to be H. That's a theorem. Again, it's not a difficult theorem, but one of the basic theorems in algebraic groups, proved early on in. Sorry. This theorem is due to Chevalier. Yeah, Chevalier. Well, all the major theorems are either due to Chevalier or Borel. All the early theorems are due to Chevalier, and some later theorems are due to Borel. There are of course other theorems which are more technical in nature. For the broad theory, the main contributors are Chevalier and Borel. Okay, so there is such a representation rho and a vector in that. Now what do? You look at the orbit map. I am going to take the case when the second group G is GLG. You have this So you look at the representation rho with that property, with a vector v naught such that h equals set of g in GLG represent over k of GLG I am assuming now that h has no characters defined over k, in which case I can actually say it is those which fix a point, because this character chi is necessarily trivial. So H is such a subgroup. Now look at the map, the orbit map GLG to V, that's a vector space rho represent on space V. Look at the orbit map G going to GB naught. Clearly this factors through, this is mapping, let me call this map F. F factors through GL G by H now. Of course, we have GL GR real points by HR VR. I am looking at the orbit map GV naught. Now, what happens to the subset? You have the subset GLGZ here, this subgroup here GLGZ. Look at f of GLGZ. This is a closed discrete subset of VR. Why? V naught, for instance, you could have taken it as a, V naught is some rational vector. When I transform by integral matrices, it's going to, the integral matrices inside here may not go into integral matrices, but will go into the arithmetic group, which will become, so denominators will be bounded, and V naught is also something with bounded denominators. So when you look at the orbit, you get vectors which are rational with bounded denominators, with a fixed bound on the denominators, which means the discrete set. It falls into some 1 by n times integral points. So the image is this discrete closed subset, closed discrete subset, and therefore GLGZ times H is closed in GLGR. It's a closed subset. Therefore, by definition, its image in GLGR by GLGZ is closed. I mean, I put GLGZ on the right, that makes no difference. You can take the inverses and convert everything. You can take inverses here, then inverse of this is closed in GLGR. So you conclude therefore that the image is closed, and already I proved it's relatively compact, so the image is compact. So image HR by HZ in GLGR by GL or SLGR, in fact it goes into SLGR by SLGZ is compact. Now notice this space is homogeneous under HR. HR acts transitively on this and also on the image. It's a bijection. This is a bijection and it's a continuous bijection. And I need only to prove it's open. this comes from a bare category argument. The idea is that take any open set here, take countable number of translates which cover that, look at the image, the countable number of translates covers that as well, and therefore there is some point which is an interior point. So for every open set, the image is the interior point. From that, it's easy to see that image has to be open. Some bare category argument is needed to conclude. Using homogeneity of HR by XZ as well as its image, get that IH HR by HZ into SLGR by GZ is a homeomorphism onto a compact therefore this quotient is compact. We still have to deal with G. H is the quotient of G by the center. The adjoint representation factors to the center. Adjoint means what? Add inner conjugation on the group, which results in a representation of the Lie algebra, which is the adjoint representation. And all the central elements act trivially on the group by inner conjugation. Therefore, add of the center becomes trivial. We have seen that G. We have assumed that G is of the form T times S, and T intersection S finite. That's the situation we have. So T times center of S is going to be the center of G. So when you take the adjoint representation, this whole center figures in the. So add G to GL of G factors through G modulo center. Now, add factors through this, okay. What we will do now is the next step is to show that the mapping.
In the previous case, you basically proved the theorem for G sample.
That, yeah, if no, not yet. If the center is trivial, the previous statement proves the center is trivial. If the center is finite, still I have not proved it, because G by GZ, that IH I said is injective. I am using the fact that IH is injective. It's a one-to-one continuous map, and I proved that it is open and therefore a homeomorphism, but from IH by IZ. But G to H, this center still exists.
But center is finite.
Center can be finite, but still that doesn't prove the theorem. You see, it can happen that GZ goes into a subgroup which is much smaller. So the question which you asked earlier, if G to H is a surjective algebraic group homomorphism, does GZ map onto an arithmetic group? And the answer is yes, but this is the crucial step in proving that statement. So I have to prove the following statement. Claim G by GZ, GR by GZ to add GR by, well, I have to be a little careful. Let me put prime here. Here I have suitable subgroup of finite index is what I know will go into GZ. Okay. the inverse image of gz contains some subgroup of finite. So this, let me put it like this, yeah. Gz prime where gz, so you have the mapping gz prime, so you have the map g2 at g, which I have been calling h anyway, and this is j, let's say, just add. So gz prime by definition is gz intersection add inverse z. We know that this is an arithmetic group because the subgroup of finite index goes into integral matrices always. There's no problem there. The problem is that the image may not be a subgroup of finite index in gz here. Huh? Add inverse of sorry, hz. I take the inverse image of the integral points here in gr and then intersect it with the integral points there. They may not be integral a priori, you don't know. In fact, some integral points may not be liftable. Only things in a subgroup of finite index will be liftable eventually. So the situation is this. Let me write G to H with some kernel C which is central. This is the picture. I take GZ here, but GZ may not map into this. These are in different. This is in some GL of V. This is in GL of G. They are through the adjoint representation. These are different vector spaces. So if I take integral matrices here, it's not clear that every integral matrix can be lifted to an integral matrix here. What you can do is to, however, in GZ, take integral matrices here, look at the inverse image. They may not be integral, but intersect with GZ. Call that GZ prime. So that maps into HZ. So you get a natural map of GZ prime, G by GZ prime, into H by HZ. But this group is arithmetic because we know that sufficiently deep congruence group, every element of GZ will go into HZ. It will go into something integral. We know that. So this certainly is an arithmetic group, and you get a natural map from here to here.
Arithmetic group in GR.
In GR, yeah, sorry.
How GZ prime is arithmetic in GR?
GZ prime you have to prove is a subgroup of finite index in GZ.
Yeah.
Now take any K morphism will take a sufficiently deep congruence group into integral elements. If you have a K morphism, it's a polynomial with coefficients in the field K. Those polynomials will be bounded, and then if you put a gamma here and take its image, the entries are Pij of gamma, where Pij are polynomials, but gamma is a deep congruence group, which means the polynomial on an element which is congruent to, all the entries will be congruent to 0 mod some large ideal, and if the ideal is sufficiently large, it will cancel out the denominators. Any morphism will take integral matrices, not necessarily integral matrices, but integral matrices bounded denominators. That's what happened. Any morphism, and if you go to sufficiently deep congruence group, these denominators will cancel out the ideal you are dealing with, which gives the congruence subgroup, will see to it that the denominator gets cancelled out. This is an argument I talked about also last time when I dealt with orthogonal groups. See, the proof is very similar. In that case, what happened was this: you had a sequence of vectors on which the quadratic form tended to 0, and then the quadratic form was integral or rational. Therefore, that cannot happen unless the elements are 0, because we also assume the quadratic form is anisotropic. Something similar, what we are doing here is with this coefficient characteristic polynomial. Instead of dealing with that special case, we could handle with value with simply using the quadratic form. Here you take the various coefficients of the characteristic polynomial, the same argument is what I have applied so far. Now this is the next thing. So you have the natural map gr by gz prime to hr by hz. You have to prove that this is also, suppose I prove this is proper, then inverse image of compactness is compact, therefore this is going to be compact. So that is the statement which I make. So gr by gz, what I call gz prime, into hr by hz prime hz, this map is proper. In fact, one can say, or equivalently, you can go all the way to GL of GR by GL of GZ. You can say this mapping is proper because we know that this is proper already. We know that this is compact and the image is compact. This is a compact space, this is a proper map. So it's enough to prove that this mapping is proper. Okay, what we will do is the following. So now let's look at GR, where G we were assuming is contained in some GL V. Okay. The group G acts on GL V, therefore the Lie algebra also acts on V. We'll keep that in mind. Or maybe I'll stop here and continue next time because it's a long proof. So so next time I will prove this claim. So please remember it and that's
Next lecture we'll have at 2:15 on next coming Monday.
Coming Monday,
2:15,
there is
2:15,
this,
yeah,
Nog memorial lecture.
I'll
2:15.
send a mail right now, or maybe
2:15 is fine.
yeah,
Okay.
2:15 to 4:15. Then
4:30 is that other lecture.
4:30 Nog memorial lecture.
Okay, so this is the basically what. Let me just say something. If you have sequence Gn in Gr which goes to infinity in GLV modulo GLVZ, suppose it does, then I will prove that it also goes to here. And because the mapping GR by GZ to GLV by GZ is going to be, that again is proper. So the two steps, if you like, the mapping GR by GZ to GLV by GLVR by GLSL. So it stays in SL because there are no characters defined over Q, stays in goes in SL. SLVZ. This mapping is proper. It's the first thing we prove. That's essentially the same as what we did earlier. We use the fact that this group is defined by as a isotropy of some line in some representation of this of SLV. You do that. So this is proper. And then secondly, you prove that if Gn goes to infinity, modulo SLVZ, then at Gn goes to infinity, modulo GLGZ. This is what you do. So that will prove the statement. These are the two steps you proved. The first step I have essentially proved already. That right, in a slightly different setup, I proved this statement. So it's really this that comes up.
so for suppose I have a torus which is anisotropic over Q, but splits over R, and then take the Z points.
Yeah.
How does it? I mean, this is going to be compact, but how to prove in the case of torus?
Yeah, this will prove it in the case of torus as well. This statement, I'm not using it. Okay.
Just wanted to understand the torus case.
See,
So how is
the torus case, I'm saying that G is a torus. If this mapping is proper, so is this mapping is what I'm saying. And so what happens is this in the case of torus, so the point is this. See here, when you look at the action in GZ, the torus acts trivially. So no sequence can push things to 0. No sequence which does the job, which has to be relatively compact here.
H is going to be, if I assume G to be torus, H is going to be trivial.
Sorry?
If I assume G to be torus, then H is going to be a trivial group.
H is going to be a trivial group. H is going to be trivial. So the action on GZ is trivial.
Yeah.
And therefore you can't get a sequence phi n tending to 0 such that Tn phi n add Tn phi n goes to 0. You cannot find such a sequence. So which means the mapping is but I am now saying if that happens, here also there can be no sequence going to infinity. Okay. So if there is a sequence going to infinity here modulo SLVZ, there is a sequence there going to infinity modulo Z, but there is no such sequence because the action is trivial for the torus. But the argument applies for G as a whole. You don't have to single out the torus. Okay.